So this video is all about using what we call the distributive property. We're going to talk about what the distributive property is, how we use it, and some ways that we're going to use it both this year and in the future. And to talk about the distributive property, we're going to start off with a swimming pool. But not just a regular old swimming pool that's created in a rectangle like this one, but let's look at something more complicated, such as this swimming pool. And the first question we're going to think about is, what's the total area of that pool? Take a second, pause the video, see if you can come up with some strategies for how you might find the area of this swimming pool, and come back when you're ready to move on. So if we were talking just about that first pool that we saw, then it would be pretty simple to find the area of that pool. It's just a rectangle, and we know that a rectangle is made up of a length and a width, and we would just multiply length times width. Well, that's great if our pool is just one area like this lap pool is, or rather maybe it's a pool at a hotel. Not entirely sure, but it's a fairly simple pool. However, as soon as we get to something a little bit more complicated, we have to start using some more sophisticated strategies. And in this case, it might make sense to break the swimming pool down into smaller pieces. Now, one way we could break it down is to draw a line straight down here and break it into the red rectangle and the blue rectangle. But as we can see, the swimming lanes go left to right, so that probably isn't the most effective way of talking about the pool. Instead, we'll split it up into the lap area, this larger area here, and the shallow water area, which is the smaller area. That way, we've covered the entire area of the pool, but we split it into nice, natural, easy sections. The lap area we know because it has those little blue or black T's at the bottom and the lane ropes to tell swimmers that they're going in the right direction. And the shallower area, we can see that there are people who seem to be sitting in it or lying down, definitely not as deep as the lap area. And so the idea that we can take an object like this and split it apart into smaller groups that make up this complete object is one of the things that we're going to use with the distributive property. Not specifically with area, but the idea that this pool, this object that is the swimming pool, is not only able to be thought of as one continuous body of water, but split into smaller sections is going to be what we're going to focus on. Because if we wanted to create a copy of this swimming pool, say we wanted to create a new swimming pool a few miles down the road because this one was really popular and we were going to create a copy of it, we would have to create copies of both the smaller area and the larger area. The two of these things together create this one object that we call pool. So if we're going to make 3 swimming pools, we need 3 of each of these objects to create 3 identical copies of the pool. And that's what the distributive property is. It's going to allow us to create multiples, or in our case this year, multiple copies of a group that consists of smaller pieces. When we get into a little bit more complicated algebra in future years, when you get into calculus, then the distributive property starts to become a little bit more complex. But this year, it's about creating multiples or multiple copies of a group. Let's look at that in one other instance. Let's say that you had a Reese's Peanut Butter Cup, or because I love Reese's Peanut Butter Cups, a half-eaten Reese's Peanut Butter Cup, and 2 apples. Now, if we were going to create lots of copies of this group, let's say that you had some friends coming over for a party and you were giving them a pack of Reese's Peanut Butter Cups and 2 apples each. Well, if you had 4 friends coming over, not only would you need 4 peanut butter cups, because you have 4 friends who are going to eat them, you would also need 4 sets of apples. So creating 4 copies of that group, Reese's Peanut Butter Cups and 2 apples, means creating 4 copies not just of the peanut butter cup, but also of the apples. Let's look at that, except this time with 2 Reese's Peanut Butter Cups and 3 apples. So together, this is our complete group. Like our pool was made up of a shallow area and a lap swimming area. If we wanted to create 3 copies of this group, well, we have 1 copy here. We would need not only to create 3 copies of our peanut butter cups, we would also need to create 3 copies of our apples. And that is the essence of the distributive property. What I'm going to show you now and ask you to pause and write down is an algebraic description of what it is. So go ahead, pause the video, copy down this expression of the distributive property, and come back when you're ready to move on. So it may look a little bit complicated with the algebra right now, but here's what's going on. In our first example, we have a, whatever our variable a represents. Remember, variables just represent numbers, either any number we want or particular numbers that we choose, and that a is being multiplied times the group in parentheses b plus c. Now, like we saw with our peanut butter cups and apples, if we're going to take copies of a group of things, we have to copy each of the smaller pieces. So not only do we have a copies of b, we'll see a number example here in just a second, we also have a copies of c. So a times the group b plus c is a times b plus a times c. We take that first number, if we imagine a is, for example, a 4, that would be 4 times b and 4 times c. 4 copies of each part of the group. The same thing is true if we happen to have subtraction. So if this a down here is a 3, for example, although we could just leave it as a, that would mean 3 copies of b minus 3 copies of c. Everything in the parentheses, every piece of the group is going to be multiplied by whatever the number on the outside is. But we're not just going to use that with numbers, because if we just had numbers together, we know how to work with our order of operations, so that we can just simplify the parentheses first. We could use the distributive property. Where it's going to be most useful to us and most useful to you going forward is when you have a variable. So this is just 2 copies of the group x plus 4. That means if we're going to create multiple sets of x plus 4, just like where we had our Reese's Peanut Butter Cups and Apples again, we need to create copies of x, 2 of them, and we need to create copies of 4. 2 copies of x and 2 copies of 4. So our answer here is 2x plus 8. It doesn't look any more simplified, for example, than 2 times x plus 4, but to use the distributive property rewrites the expression without parentheses, as in this case 2 terms, 2x plus 8. So that's what we're after at this point using the distributive property. The same thing is true if we have a negative number on the outside of our parentheses. It's just negative 2 being multiplied by each of the numbers in parentheses. So negative 2 times x, which is negative 2x. We're still adding things together, and we have negative 2 times 5, which is negative 10. So this is either negative 2x plus negative 10. We can also write it as negative 2x minus 10. They are equivalent expressions. They mean the same thing, and we just have to be comfortable with the idea that our answer is not going to look like one specific number. So go ahead, pause the video. We've got 3 pages of distributive property for you to work on, 2 problems each. Pause the video, work on these, come back when you're ready to see the answer. Remember, you're not going to end up with a single number. You'll end up with an expression without parentheses. So in our first one on the left, we have 3 times the expression x minus 7. That gives us 3 times x, which is 3x, and 3 times 7, which is 21. We just keep that subtraction sign in the middle. On the right, we have negative 4 times g, which is negative 4g. We have negative 4 times 9, which is negative 36, and we're adding them together. So negative 4g plus negative 36, or as we said before, you can write that as negative 4g minus 36 if you prefer. Either way is correct. Next 2 set of problems, go ahead, pause the video, work on these, come back when you're ready to move on. So for the one on the left, we have 5 times each of the pieces of x minus y. So 5 times x is 5x. 5 times y is 5y. And we are subtracting them, so it will be 5x minus 5y. In the problem on the right, negative 8 times x is negative 8x. Negative 8 times 4 is negative 32. And again, either negative 8x plus negative 32, because we are adding them, or rewriting it as negative 8x minus 32. Finally, one last set of problems. Go ahead, work on these, pause the video, come back when you're ready to see the answers. On the left, we have 7 times each of x and 3y. 7 times x is 7x. Now, 7 times 3y is a little bit interesting, but 7 times 3 is 21. and y just is y. So 7 times 3y is 21y. We're subtracting, so it's minus 7x minus 21y. And on the one on the right, it's not a number that we have outside the parentheses now, but the same idea holds true. We're creating x copies, however many that happens to be, of the expression 4 plus 2y. So it's 4x times. I'm going to write 4x instead of x4. And 2y x times, which gives us 2 times y times x. And that's fine, because we can have that being added together, and that's our answer. So again, the distributive property just allows us to create copies of an expression in parentheses, whatever it's being multiplied by. Every piece of that term, of that expression, gets multiplied by that first number, or divided if we happen to have division, just like if we're making copies of peanut butter cups and apples.